Hey engineers, and welcome to 2.3.1, which is material testing. In 2.3.0, you guys got an introduction, a really fast and furious introduction to stress and strain and how brittleness, ductile, toughness, strength, all of those things play into account with engineering. And to get us started today, I wanted to show you a video. And this has always helped me when I fly. If you guys have never flown on an airplane, a lot of people get really nervous about flying. And I kid you not, this video has comforted me for over, I think, at least 10 years. Check it out. This is a wing loading test for a Boeing 777.
777 wings could survive the strongest forces that turbulence.
So what they do, they take a Boeing and they just pull on the wings until they break, and it's impressive.
Bad handling could produce. They were also interested in whether the same wing design could be used on future, heavier versions of the plane. It would be a simple question to answer, using a plane specially built for the purpose. They would just attach strong cables to the wings and pull upwards until they broke.
So you can see him pulling the ends of the wings very slowly.
The force on the wings became so strong it caused ripples in the fuselage. The engineers hoped
the outside of the actual what people are saying.
50% of the strongest forces it would ever meet in flight. They predicted a wing deflection.
There's a huge crowd of people gathered around to check this test out because they don't do it all the time.
Main retention, we're now holding at 120% design limit load. We'll again make a load check.
Drama here as they're pulling, and then you just see how far these wings. Can you see the wing right here? Like how far this thing is up in the air? So they're all cheering because they designed it to withstand twice the amount, I think. There's some factor of safety that they have in here. And they've exceeded their factor of safety. So these engineers and designers are super excited. But look at how far this wing has been pulled.
153. 153.
So every time I fly, you look out the window and you're going through turbulence, or people are like, oh my gosh, or you look at the wings and they're flapping a little bit. It's like those wings they could go 20 more feet and be totally safe. So this video and the idea behind the material testing has literally comforted me ever since I've seen it and I've flown. So as you fly, think about material testing and what's gone into that, and it might bring you a little bit of comfort. Material testing, you should be able to reproduce it. There's two types. There's a static test where it's just constantly loaded. So that's what you saw there. It's a constant loading. Or you could have a dynamic test. Maybe you want to cycle this thing to see how many times this switch can function, how many times this straw can bend, how many times this laptop can open and close. Some of the things that we test for, how strong it is, how far it can stretch, when it fractures, how does it fracture, and then does it meet the design requirements that are specified. Some of the things that standardized tests we have are tensile. It's when you pull it, and then the compression test, you're squeezing it until it fails. Or there's a hardness test, and you saw the tensile test and the hardness test in our previous video where they pushed that diamond tip for the Rockwell hardness test. There's other types of testing besides Rockwell that we'll talk. A tensile test, you basically just, in one axis, in one direction, you pull it until it fails. It's destructive, meaning that you pull it until it physically breaks. Here you can see this is where the specimen goes in this testing thing right here. There's a hydraulic pump that drives this whole thing. And then there's a graph right here that will actually produce that stress versus strain curve that you saw from our first video. This is the typical type. They call it a dog bone. sample, so you put threads around it, and then you physically will machine away a small amount on the inside. They'll do that on purpose so they can make sure that it breaks here. It will break in the skinniest spot. So they will physically lathe this down until you get a smaller part, so you can make sure that it breaks right in the middle. The samples that we have at school, this is what they are. They're 3 inches long with a 1-inch piece on the inside. There's a 1/8 inch fillet, which this is called right there. You've got 1 inch of barrel, 1/2 of an inch of threads on either side. So it's very structured, 1/2 inch, 1/2 inch, 1 inch, 1/2 inch, 1/2 inch. Your tensile test, you end up getting this graph, which you saw in our first one. We apply a force, F, and then this is the Greek letter delta. Maybe you're used to seeing the capital letter delta. The capital letter delta is that triangle. This is the lowercase delta, and delta always means change. So this delta represents the stretch, how far it stretches. So how hard are you pulling? How far does it stretch? And you get this general curve for most materials. The thing is, if you test 2 different materials, both of these are being made out of brass. But the thing is, if you apply the same force to them, they're going to be stretching different amounts. Because if you have a bigger dog bone, it's not going to stretch as far because it's tougher. So we can't use force and we can't use stretch. So this is where the idea of stress and strain comes into this, is that we have to take the force divided by the area. And so if you take 100 pounds to both of these, 100 pounds on 1 square inch or 100 pounds over 2 square inch, here you've got 100 psi and here you've got 50 psi. So that becomes relatable using the areas. So we define a unit called stress. It's basically force. So how much force you're pulling on something, and you divide by the area. So that makes it uniform across no matter how big your test sample is. You could have a big fat test sample, or you have a real tiny skinny one, and the stress is going to be the same because you're going to take the force and you're going to divide by the area. So it keeps everything the same. It says calculate the stress in the dog bone with 430 pounds. So let's figure that out. So if I'm going to figure out, so we're going to find the stress on this here. So the stress, this is the stresses, that delta, how long it stretches. I'm sorry. Let me have to go back. I got to check this out. I think stress is sigma. I wanted to get the right symbol. It's force divided by area. So the force that we're pulling is 430 pounds. And the area, it's this area of that dog bone right there, or pi, times the radius. And this is the diameter. If you look at how this is drawn here, that's the diameter. So it's half of that, 0.0625 squared. So when you do all that, you get 0.0122. Now, units. This is in pounds, and this is in inches, and that's inches squared, so it's pounds per square inch. So the units of stress are PSI. How many pounds are you pulling over how many square inches? PSI. Strain. Strain is that boy, I had to go over here and I forget these letters. Strain is right here. It was epsilon. Nope, there it is. So there's epsilon. And you saw delta before. Delta means we're used to seeing the triangle, meaning change in temperature, change in time, change in whatever. But this is the lowercase. So here we've got epsilon that represents strain. And elongation. So strain is, it's kind of like how we did it with force, in that it was force divided by the area. this stretch, how far it stretches, it's a proportion of how long it was to begin with. So if something was like 40 feet long, it's going to stretch a whole lot, you know, or if something was 1 inch long, it's going to stretch a tiny bit. So it's a proportion of its total length. So strain is equal to the amount of stretch, so the elongation, so how far it stretches, that's delta, divided by the original length, L naught, L sub 0. So here's a dog bone that stretches that's 1/16 of an inch, 0.0625. So the strain, epsilon, or sometimes people will do it like this. I think I'll typically do it like that. It's equal to how far it stretches, delta, divided by its original length. So it's stretching 0.0625 inches, and then its original length is 1 inch. So this is the length that we're testing. This part right here, not the whole thing, because this is the part that's got the 1/8 of an inch. So we're going to divide that by 1. Ha! This is a nice, easy math problem. So this is 0.0625. And these units, you'll notice that inches cancel off inches. So this strain doesn't have any units. It's a proportion. Not PSI, not anything else. It's inches divided by inches, or just a percentage. So the thing stretches 6.25 of its original length. Our tensile stress versus strain curve. You saw that in our original video. I'm going to move this over here. This part is linear. We call this the elastic region. Stress and strain are proportional, meaning that if you pull with twice the amount of force, then you're going to get twice the amount of stretch. Pull with 4 times, you get 4 times the amount of stress. That's what they mean by it's proportional. We call this the elastic range. It's called the elastic range because if you let off, it will go back to its original shape. Like we talked about a rubber band. If you let go of the rubber band, it goes back. Metal does the exact same thing. If you pull it, it will go back unless you pull it too far. Maybe you've played with a slinky and you went too far, or a paper clip where, you know, it's got that elastic region where it will clip the papers, but if you bend it too far, oh shoot, now it's not going back to its original length. The proportional limit right there, the stress at which it's no longer linear, meaning that it's kind of very close to the yield point. To me, I don't know the difference between them, but they're really close to one another. The modulus of elasticity, it was called Young's modulus in that video. It's the slope of this line, stress divided by strain. So you'd find the slope of this, and that would be the modulus of elasticity. Rise over run. Stress divided by strain. Rise, stress, divided by the run, strain. Look at all these letters. Oh boy, modulus of elasticity, letter E. Remember that number right there? Sigma? Nope, this one's sigma. This one's, oh boy, what was that one? Delta? Not exactly sure. We'll look it up. Okay, so here's a picture showing that if you remove the load, it will stretch back to its original length. This is called the elastic region. The elastic limit, it's really close to the proportional limit, which you just saw. To me, there's no difference really in any of them. Resilience, the amount of energy, and we talked about the toughness, right? The area underneath. It's the area underneath here. So you would find this area, or the this area. Not exactly sure, but it's going to be the area underneath. Part of me thinks that it's under the elastic region because that's kind of where we're never really taking. This is, for all intents and purposes, in engineering, this is failure. when things start stretching and they don't come back to their original length, like we don't like that, and we just let it go. So my thing with resilience, you're going to be this area over here. Yep, sure enough. Again, why is it important to designers? Once things stretch past, they don't come back. We don't like that. Again, yield point, these things are all next to each other. When the material yields and you pull it, it becomes easier to pull, and it stretches. Offset yield strength. Don't know why this defines the stress required to produce a tolerable amount. So a little bit of pull is okay. If you go beyond it, they're like saying, oh, you can go 2% beyond it, or like 0.2% beyond. That would be acceptable. But I don't exactly know the point of that one. Plastic deformation. So over here, this was the elastic region. Now we get into what's called the plastic region, plastic deformation. When you pull it, it's no longer going to go back. Unrecoverable limit. Represents failure. We talked about that before. So what this means is that in this region, you still have to pull harder. You're still having to exert more force. I still have to pull harder. But now over here, I don't have, it starts pulling further, and I'm using less force. So my force, less force. More force. Maybe you've done that with a paperclip where you start you're like wiggling. Okay, it's really easy to wiggle at the end just before it breaks. Load bearing increases. They call it's work hardening. You're heating that material up, which actually tempers it a little bit to make it a little bit more harder. The weakest point, we call this the ultimate tensile strength, the maximum amount of force that it can withstand. This is called necking. Just before failure, you're going to see this in tension. Necking. More ductile the material, the skinnier this will get. The more brittle a material, it will just pull apart. Like you'll see cast iron just pop in half. Or then you'll see aluminum just really neck down to almost nothing. Copper and gold, like gold is super malleable. You'll watch that thing really go. Failure. This is where it breaks. When you pull ahead, when it pulls apart in two, that's the ultimate amount of distance that you can pull, because remember, strain represents distance, how far you can pull it. And here you can see cast iron, that flat cross section, and here you're getting that real big necking going on right there by something, and kind of a medium amount of necking. Brittleness, so how far something can stretch. So like this did not stretch very far. This material stretched a whole lot, and we call that brittleness. The ability for it to be stretched a long distance without having to break. Toughness. This is the area under the entire curve. Because what was that other area? It was something like, I forget, a few slides ago. Resilience. So resilience represents the area underneath the working part of it, the elastic region, and then toughness represents the whole area. So something can be tough and not resilient, or resilient and not tough. They're a little bit separate. Compression. Instead of pulling things apart, we can squeeze them together. Hardness. You guys, we looked at the Rockwell hardness, but there's a Brinell where they take a ball, a tungsten carbide ball, so they press a ball in and they just measure the width of the crater. And then the Rockwell test, that diamond tipped cone, which you saw in the video, and the depth is measured. And there you have it. Whew! Thanks for paying attention, kids. Got a lot of words, a lot of definitions to get in.